this video, we're going to talk about graphing polar equations. So in the last video, we introduced polar coordinates. We also talked about how we could convert polar coordinates to rectangular coordinates since we're familiar about graphing in rectangular coordinates x and y. Well, we don't actually need to do conversions in order to graph polar equations. Just as with x and y, polar equations can be graphed just from their structural standpoint. So if we know what the structure of the equation is, that's going to indicate what kind of graph we can expect. And we can also graph by plotting points, which is what we do with rectangular coordinates as well. So polar equations can be graphed by plotting points, specifically where we think of theta as the input. So our rotational component represents the input. And then r, our directed distance, that's going to be represented as the output. So it's kind of counterintuitive because when we write a polar point, we write r first and then theta second. Still, we think of theta as the input and then r as the output when we're graphing. So as with anything in rectangular coordinates, the equation's structure represents or indicates the graph's shape. So just like we make generalizations about what a graph is going to look like in x and y just based on what we see, if x and y both have exponents of 1 and everything's polynomial, we know it's going to be linear. If x is squared, typically it's going to be a parabola. Those kinds of generalizations. We can make those same generalizations when we talk about graphs for polar equations. Based on how the equation is structured, we know the graph will have a certain shape. Now, as theta increases, in other words, we start from 0, and as theta gets bigger from there, we can determine the direction in which the graph should be traced. Now, when we're talking about polar coordinates, there's innate rotational component associated with polar coordinates. So there will be a particular direction in which we rotate based on theta increasing. So one thing we have to keep in mind in terms of rotation and based on the complexity of the equations we see, some graphs can be traced and completed in less than a full rotation. In other words, if we were to look at radian measures all the way from 0 to 2 pi, look at values for theta all the way from 0 to 2 pi, we may find that by going all the way from 0 to 2 pi, we end up retracing some of the points we've already graphed. That means the whole graph is completed in less than one full rotation about the unit circle, if you want to think of it that way. Now, some graphs, you will need more than a full rotation in order to trace them. It's just going to depend. Typically, the more complicated the function is, if we have a trig function that has maybe a multiple of an angle inside of it, something like that, those are the kind of equations where you can expect that the graph may take more than 0 to 2 pi in order to trace, just based on what we know about those kind of situations. We know whenever we multiply theta by a constant inside of our trig function, that changes the period of that function, which means it may take less time, it may take more time in order to trace the entire graph. So it's just going to depend. When in doubt, though, it's all plotting points. Just like when you learn to graph in x and y, you plot points. You pick an x value, you find the y value, you plot the point, and you keep doing it until you have a sense of the shape of the graph. We do the same thing with polar coordinates. We just have to graph the points a little bit differently. So you're going to want to have your graphing calculator handy so that finding these ordered pairs is going to be a little bit easier and graphing is going to be quicker. Okay, so let's start with some basic types of equations. And we're going to go based on examples. So rather than generalizing and then graphing using examples, it's helpful to just work off of an example and then generalize what we see based on the structure of the equation we just graphed. So for our first equation, we have theta is equal to 5 pi over 3, and we want to graph by plotting points. Now, what does this mean? It means that our theta coordinate, our rotational coordinate, is 5 pi over 3. Now, what about r? Because we don't see an r here, it means that r is independent of theta. In other words, the distance we travel is not impacted by how far we rotate. We have to be rotated to 5 pi over 3, but r can be anything we want. So what would this look like? Rotating to 5 pi over 3 starting from the polar axis. Well, here's 5 pi over 3. Okay, so everything we graph is going to be along the 5 pi over 3 ray in our polar plane, but r can be whatever we want. So what if r is 0? Well, if r is 0, r equals 0 is another name for the pole, that original point there in the middle, what we think of like the origin in the xy plane. Now what if r is 1? Well, that means we're going along theta equals 5 pi over 3, but we're going out to the first ring. So we would be on the first ring along that ray. If r were 2, we'd still be along that ray, but we'd be out at the second ring. If r were 3, we'd be at the third ring, and then so on and so forth. Now, we also have to keep in mind that r can have negative values. So what if r were -1? Well, that means we're along this ray, but we're tracing along the opposite side, so directly opposite in the negative direction. So 5 pi over 3, but -1 would take us back over here. -2 would take us back over here. -3 would take us there, and then so on and so forth. So you can probably tell what we're graphing. We're graphing a line. So in this case, the graph is going to be the line that follows that ray at 5 pi over 3. So anytime we have an equation of the form theta is equal to a constant number, typically it's going to be something like this, a radian measure where we can graph that radian measure. That represents a line, but specifically a line that passes through the pole, what we think of as the origin there in the polar plane. Okay, let's look at another equation structure. What happens if instead of only having theta, we only have r? Well, again, in general, that means the two coordinates are independent of one another. In this case, we're being told that r has to be -3 in every case, but theta can be whatever we want it to be. Theta can vary. So we choose a value for theta, but we have to have an associated value of r is equal to -3. Okay, so suppose we let theta be 0, which means we're along the polar axis. We haven't rotated anywhere. If theta is 0, but r is -3, that means we're technically starting over here along the negative polar axis. So this would be theta is 0, but r is -3. Now, if we allow theta to increase, so suppose we go from theta equals 0 to theta equals pi over 4. R still has to be -3, which means if we're on the pi over 4 ray, but r is negative, we're going in the opposite direction, out to the third ring. So that would take us right here. Okay, suppose we keep rotating and theta is pi over 4. I think I said pi over 4. This should be pi over 6. If we're at pi over 4, but r is -3, we go in the opposite direction, -1, -2, -3. Suppose we keep rotating and theta is pi over 3. Well, if r is -3, again, that means 3 units in the opposite direction out to the third ring. And then if we kept rotating up to pi over 2, theta is pi over 2, but if r is -3, we're going in the opposite direction out to the third ring. And you can probably see the pattern. Every single time we graph a point, it's going to be a point along the third ring. So if we were to continue all the way around out to 2 pi radians, we would come full circle, and literally we would be graphing a circle. But notice in this case, because r is negative, it means we're not starting along the positive polar axis. It means our first point starting from theta equals 0 starts along the negative polar axis. But otherwise, we're just graphing a circle, specifically a circle centered at the pole with a radius of 3. So not very pretty, but you get the idea. There's the equation of our graph. So generalizing, anytime we have an equation of the form r is equal to a constant, that represents a circle specifically a circle centered at the pole. And whatever the value is for our constant, that's going to be the radius for our circle. Essentially, it tells us which ring we have to go out to in our polar grid. Now, let's add in r and theta together. So what happens if we have something of the form r is equal to a number times theta? So here we have r is equal to 2 theta. If we didn't have a 2, we just had r equals theta. We just think of it as a coefficient of 1. We can have any coefficient we want, and we're going to see the same behavior. Now this is where the calculator is going to probably be handy. So again, think of theta as your input. We're picking values for theta, and we're solving for the associated value of r. Now we graph in radians. Theta is in radians. So for now, we're going to have to make sure we use radian measures. Okay. So r is equal to 2 times theta. I'm going to go to my mode, make sure we're in radian mode. Okay. Here it's not ultimately going to matter because we're really just multiplying. It's going to matter when we have a trig function involved though. So suppose theta is equal to 0. Well, 2 times 0 is 0. So if theta is equal to 0, r is equal to 0 as well, which means we're right there at the pole. It means that's our starting point. Now, suppose we increase theta to pi over 6. Well, r is going to be 2 times pi over 6, which is going to be a little bit more than 1. So you're just going to have to ballpark it. You're going to find a lot of these nasty looking irrational numbers. Just ballpark it. What we know is that the measure for r is between 1 and 2, but much closer to 1 than it is to 2. So when theta is pi over 6, we're right past the first ring on our polar grid. So about right there. Now if we keep rotating, go to pi over 4. Theta is pi over 4, and r is going to be 2 times pi over 4, which is about 1.6. So there at pi over 4 radians, r is going to be about halfway between the first and second ring. Now if we continue rotating, rotate to pi over 3, r is going to be 2 times pi over 3, which is a little bit further out than 2. So when theta is pi over 3, r is just a little bit further out than the second ring. Okay, what happens when we get to pi over 2? R is going to be equal to 2 times pi over 2, which is about, or exactly in this case, pi. So 2 times pi over 2, your 2's cancel, you're just left with pi, which we know is just a little bit further out than 3. So when we're at pi over 2 radians, we're on the 1, 2, 3, just a little bit past the third ring. And you may start to have a sense at this point of what's happening. If you trace the points in order, what's happening? Well, let's go a little bit further out. So what happens if we rotate past pi over 2 and then go to 2 pi over 3? Well, r is going to be 2 times 2 pi over 3, which is going to be a little bit past the fourth ring. So at 2 pi over 3, 1, 2, 3, 4, just a little bit past the fourth ring. If we keep going, get to 3 pi over 4, r is going to be 2 times 3 pi over 4, which is about 4.7. So at 3 pi over 4 radians, we're really close to the fifth circle. So 1, 2, 3, 4, close to 5, about right there. And then if we go to 5 pi over 6, let's see what happens there. So r will be 2 times 5 pi over 6. Oops, my bad, that should be divided by. 2 times 5 pi divided by 6. There we go. And about 5.2. So notice we fall off the grid. So if we want to graph it just a little bit further out than there. And of course, past that we'll continue outside of our grid. So what's happening here? Well, keep in mind we're starting there at the pole, but what's happening is we are spiraling. So we're rotating but we're rotating in such a way that each time we rotate further, our distance also increases, in this case by a factor of 2. So we're rotating around, connect your dots. It doesn't have to be perfect, just do your best. And so we have something that's structured like that. So anytime we have an equation of the form r is equal to some multiple of theta, notice there's no trig value present yet, we're just talking about r and theta, that is going to represent a spiral. So the higher the value for a, our coefficient, the faster it's going to spiral out of the grid. Now notice in this case a was a positive number. A could also be a negative number. So if we have a positive number, we're rotating counterclockwise. If we have a negative number, you're going to find that we rotate clockwise instead. So this particular form of an equation is going to give us a spiral when we graph it. Okay, let's look at a couple of additional ones. Add in a trig function, what we're used to seeing. So let's do 2 and 1 and see if we can generalize what we see from both of these. So for our first one, let me clear out that. We have r is equal to 4 times the sine of theta, and r is equal to negative 2 times the cosine of theta. We want to graph these on the separate grids. Now here, normally we think of our theta as being in terms of radians, and technically speaking it is, but for purposes of typing things into the calculator, we're typing in our angle measures, our values for theta. It's typically quicker to type in degrees. So I'm actually going to change my mode to degree mode just to save myself a little bit of time with typing. So in this case, what we're thinking of is 0 degrees, 30 degrees, 45, and 60. So the amount of rotation. And then when we plug in our value, the sine of pi over 6 and the sine of 30 degrees, they're going to be the same thing. So the amount we get, the number we get for r is going to be the same. It's just going to be a little bit quicker to type in 30 degrees than it is to type in pi over 6 and then pi over 4 and then and then pi over 3 and then so on and so forth. So I'm going to type in degrees just to save myself a little bit of time. But keep in mind, typically we give theta in radians instead of degrees. Okay, so we're starting at theta equals 0. So for r is equal to 4 sine theta, what is r going to be? Well, r is going to be 4 times the sine of 0, which is going to be 0. Okay, so at 0 rotation, 0 degrees in this case, our associated value for r is also 0, which means we're at the pole. We're starting from the pole. Okay, now what happens if we rotate? So suppose we rotate to pi over 6. So that's going to be 4 times the sine of pi over 6, or in degrees, 30 degrees, which takes us to 2. So when we're at pi over 6 radians, or 30 degrees, we're on the second ring. Okay, let's keep going. So if we rotate around to pi over 4 radians, or 45 degrees, 4 times the sine of 45 degrees is going to be an irrational number, so about 2.8, so close to the third ring. So 45 degrees, first, second, third ring, close to that third ring, somewhere around there. Okay, what if we rotate to pi over 3 or 60 degrees? So 4 times the sine of 60, about 3.5. So 60, 1, 2, 3, about 3.5. So roughly there. And then let's keep going to 90. Pi over 2 radians, or 90 degrees. So 4 times the sine of 90. Well, we know the sine at 90 degrees is going to be 1. So 4 times 1, not unexpected, is 4. So at 90 degrees, we're at 1, 2, 3, the fourth ring. Now what happens as we keep rotating? So it looks like maybe we've got half the picture. Let's get as much as we can. Keep going. So now we are at 2 pi over 3, otherwise known as 120 degrees. So 4 times the sine of 120 degrees. It's going to be about 3.5. So compare this to the output we got from before, 4. Notice it's the same value. That's not a coincidence. We're going to find that there's some symmetry with this kind of graph. So once we get to 120 degrees, we're at about 3.5. So about there. Keep rotating. That would take us to, what would that be? 90 plus 45 would be 135. So 4 times the sine of 135 degrees. And again, notice we get a repeated value. So about 2.8. So somewhere like that. Okay, keep going. From 135 to an additional 30 from that, that's going to be 150. So 4 times the sine of 150 degrees, it's going to take us to 2, so 1, 2. Again, notice it's another symmetric point. What happens if we get to 180? So 4 times the sine of 180, and that takes us to 0. So notice we get back to where we started. So what's happened so far? Well, we started here, we've rotated around in this manner, so you can probably see the shape that we traced. And again, you don't have to be a great artist, but try to graph carefully. It looks like we've drawn a circle. Now, to be sure this is the whole story, ideally we want to keep rotating and just verify that we don't get any additional new points. So if we rotated past 180 degrees, another 30 degrees, that would take us to 210. So what happens there? So 4 times the sine of 210. Okay, well notice we get a negative value. So what would that graph as? Well, we've gone to 210 degrees, or 7 pi over 6 radians, and now we're at negative 2, which means we're along this ray, but we're going in the opposite direction, negative 1, negative 2. And sure enough, it gives us a point we've already graphed. So what that indicates is that once we come full circle from 0 to 180 degrees, or 0 to pi radians, we then start retracing the values we already graphed. So what that means is that this particular equation, all of the necessary points are going to be plotted just within half a rotation. If we were to make a full rotation, essentially that just double traces all of those points until we get back to where we started. So this is going to be our graph. Now let's change up the trig function. So let's graph a cosine, and now I've also made the coefficient on our cosine negative. So let's see what happens there. Now again, I'm going to plot using degrees just because they're a little bit easier to type in. So when theta is 0, r is going to be negative 2 times the cosine of 0. So when theta is 0, we're at r is equal to negative 2, which tells us we're starting over here. Okay, rotate to pi over 6 radians, or 30 degrees. So negative 2 times the cosine of 30 degrees. Negative 1.7, okay, so at 30 degrees, careful, we have a negative r. So along the opposite ray, between negative 1 and negative 2, but closer to negative 2. So about right there. Just ballpark it. Now, if we continue rotating to 45 degrees, pi over 4 radians. So negative 2 times the cosine of 45 degrees, negative 1.4, okay? So we're at 45 degrees, but we're going in the negative direction, so opposite side. So somewhere between 1 and 2, just a little bit closer to 1 than to 2. Okay, if we rotate around to 60, or pi over 3 radians, negative 2 times the cosine of 60 degrees is negative 1. So there at 60, opposite side, we're at negative 1. Okay, and then once we get to pi over 2, or 90 degrees, negative 2 times the cosine of 90. Well, we know the cosine at 90 degrees is going to be 0, so negative 2 times this value, sure enough, gives us 0. So even though we're graphing over here, keep in mind the associated angles were 0, 30, 45, 60, and 90 degrees. So the reason we ended up outside of that first quadrant is because our values for r were negative, which resulted from multiplying by that -2 right there. So where are we? We're at 90 degrees, so keep rotating. So 120, 135, 150, and then 180. We'll see what happens. So -2 times the cosine of 120 degrees is going to take us to +1. Okay, so now our outputs are positive. So we've made it around to 120, and we're along the positive grid ring. So +1. Notice it is symmetric to the point below it though, just like we saw some symmetry with these points as well. So let's keep going. -2 times the cosine of 135. And that's going to be 1.4. Again, notice a similar value to the one that's kind of about half cut off above that. So at 135 degrees, or 3 pi over 4 radians, we're at about 1.5, just a little bit less than 1.5. Okay, 150, so -2 times the cosine of 150. 1.73. You'll notice that's also a repeated value if you looked back at your old outputs. So 150 degrees, we're at 1, really close to 2, getting there. And you can probably guess what's going to happen when we go to 180. So -2 times the cosine of 180 degrees is going to take us to 2. So 180 degrees, 1, 2. And so we come full circle. And just like with this previous one, if we continue, we're just going to continue tracing the same values. So keep in mind, where did we start? We didn't start at the pole in this case. We started at this particular location. So we're going to rotate around, then we hit the pole, and then we rotate back around and we have some symmetric points. So notice we also graph a circle. These circles are oriented differently though. But anytime we have an equation of the form r is equal to a constant times cosine or a constant times sine, this is always going to represent a circle. Notice it's not a circle that's centered at the pole, but it does emanate from the pole. The pole is going to be one of the points on the circle. So if the function is cosine, the graph is oriented along the polar axis. Or if we want to think of it, we can think of that as the line theta is equal to 0. We now know that represents a line. Now in this case, this particular circle was on the opposite side of the polar axis. That's because our coefficient was negative. So if the coefficient is negative, it just graphs on the opposite side of that axis. Now if the function is sine, the graph is oriented along the line theta is equal to pi over 2, which is going to be this line right here. So the circle is oriented along that line. If we'd had a -4 instead, it would just be oriented along the opposite side, but again, we'd still have it emanating from the pole right there. So in general, anytime we see an equation of one of these two forms, we know we're going to have a circle. Now, the difference here between what we saw with the other type of circle, we graphed another type of circle. R is equal to a number also graphs as a circle, and that value tells us the radius of the circle. Now notice in this case, the coefficient doesn't give us the radius of the circle, it actually gives us the diameter, the full distance from one side to another. So the coefficient was 4, we had a circle of diameter 4. Here the coefficient is -2, we had a circle of diameter 2. So still a circle, but a different kind of circle. The equation gives us a different structure. Now, as our equations get more complicated than this, we can still plot points, but we want to look for time savers, because you'll notice in all of these situations, we didn't really need to go past 180 degrees or pi radians. As the equations get more complicated, we may need to go past those values in order to trace the whole graph. So anything that can save us time so that we don't have to manually plot all these points is going to be beneficial. So one of the time savers we have, aside from just knowing what sort of structures to expect, is this idea of symmetry. Just as equations in x and y have potential symmetries, so do equations in polar coordinates. So in situations where the function that we're graphing becomes increasingly complicated, symmetry will assist us in graphing. If we know our equation has a particular type of symmetry, then generating points is kind of a 2-for-1. If we find one point, we know there may be a symmetric point to that. Now, polar functions can have up to 3 different types of symmetry. Now, the way our symmetry tests work for polar equations is a little bit different than how they work for equations in x and y. For equations in x and y, you either pass a test or you don't pass a test. This is not necessarily going to be the case with polar coordinates, and I'll explain in just a minute. So for an equation in polar coordinates, if the indicated substitution, so we're going to do a substitution, just like we do with x and y symmetry, if the indicated substitution produces an equivalent, a matching equation, once we simplify things down, then that indicates that our graph has the indicated type of symmetry that we're testing for. So our 3 different types of symmetry, we have symmetry with respect to the polar axis. So that is kind of like x-axis symmetry. Here's our polar axis. Any equation with symmetry with respect to the polar axis, we have points that match above and below. So this particular graph has symmetry with respect to the polar axis. All of the points above are matched by points below. Now, how do we know just looking at the equation whether or not we're going to have this type of symmetry? We're going to replace r and theta with r and negative theta. So if we can take our equation, substitute in a negative theta, and simplify the equation in such a way that the simplification is exactly the same as the original equation, then that's an indication that we have this type of symmetry. Now, another type of symmetry is with respect to the line. Theta is equal to pi over 2. So that would be kind of like y-axis symmetry. This particular graph has symmetry with respect to theta equals pi over 2. Or think of it as this whole vertical line. Again, what kind of looks like the y-axis. We have points to the right, and they're matched by points to the left of that line. So this particular equation has that type of symmetry. Now the test here, we're going to replace r and theta with r and pi minus theta. So not just a negative theta, but pi minus theta. If we can substitute this into our equation and produce an equivalent equation, something that matches the original, then that's our indication that we have symmetry with respect to this line. Now, if you imagine subbing in something like that to, for instance, these functions, you'd have a sine of something minus something else, a cosine of something minus something else. There are some shortcuts for simplifying something like that, but in a lot of cases you'll find you'll need to use the sine and the cosine difference formulas. So anytime we take the sine of something minus something else, or the cosine of something minus something else, we have identities, we have sum and difference identities that are going to allow us to simplify something like that. So keep that in mind. We'll see that in just a minute. And then our last type of symmetry is symmetry with respect to the pole. The pole is our name for the origin on the polar plane. So polar symmetry looks like origin symmetry. Think of it as a diagonal symmetry. That would mean we have symmetry both vertically and horizontally. And it's going to be fairly rare. We're going to determine that. It is fairly rare, but occasionally we will find an equation that has that type of symmetry. So we're going to replace r and theta with negative r and theta. And we'll find, again, in most cases, this particular symmetry test is not going to yield an equivalent equation, which means not that failing a test does not indicate that we don't have that type of symmetry. I definitely want to talk about this. When we pass a test, if we can produce an equivalent equation, that means we have that particular type of symmetry. But a failed test, in other words, we plug in whatever we need to plug in, and we can't generate an equivalent equation. that does not indicate that our graph doesn't have that type of symmetry. Instead, what it means is that the test is inconclusive. What we're going to find is that there are certain situations where we perform one of these symmetry tests and the test fails, but when we graph the equation, it does actually have that type of symmetry. So it seems like the test is contradicting itself. Sometimes the tests fail, but we still generate an equation or a graph that has that particular type of symmetry. So getting a passing test is beneficial, but failing the test does not necessarily mean we don't have a specific kind of symmetry. It just means that that test didn't give us information that it was inconclusive. So we do need to keep that in mind as we graph. But the benefit of getting a passing symmetry test, at least one of these tests, is the fact that we essentially get a 2-for-1 with our points. So for instance, if we were to test this particular equation for polar axis symmetry, it's going to fail that test. Now again, a failed test doesn't mean it doesn't have that type of symmetry. It means the test was inconclusive. But this graph, as we see for this equation, does not have polar axis symmetry. So it's not going to pass the polar axis symmetry test. Now, if we applied the test for theta is equal to pi over 2 for this equation, we'll find that it passes. So if it passes, how does that benefit us as we graph? Well, we still have to plot some points, so we'd still find this point first. This would be the second point we find as we rotate to pi over 6 radians. If we find this point and we've already performed a symmetry test and we know that we have symmetry with respect to theta is equal to pi over 2, then automatically we can generate this second point from this point that we initially plotted based on the fact that we know we have a particular type of symmetry. So it's going to save us some time in plotting points. Essentially, these 3 points will give us enough information to plot those 3 points as well, since we know we have a particular type of symmetry. So having some symmetries involved is going to be a bit of a time saver, at least in generating the actual points that we want to plot. So for the next few examples, we want to test our equations for symmetry, and then of course we will have to plot some points in order to get the graph started, but once we know about the symmetry of the graph, we want to use that symmetry in order to save us a little bit of time for graphing. And then of course we're going to generalize these structures again, just based on the kind of equation we're seeing. Okay, so we want to test each equation for our 3 types of symmetry, and then use any symmetry we find, and point plotting of course, to graph the equation. Okay, so we have r is equal to 2 minus 2 times the sine of theta. So if it were just 2 sine theta or negative 2 sine theta, we'd know what to graph because we just graphed it. But notice we now have a constant involved that doesn't have an associated trig function. So 2 minus 2 sine theta. The thing to pay attention to here, though, is that these 2 values are the same. One is negative, but it's a 2 and a 2, which is going to be important from the standpoint of how this graph looks. So we want to test this equation for symmetry before we actually start plotting points, just to see if that can save us a little bit of time. So our first test, symmetry with respect to the polar axis. We're going to do a substitution. Specifically, we're going to take our theta and we're going to replace it with negative theta. R we're going to leave alone. So I'm going to take my equation, and where I have a theta, I'm going to replace it with a negative theta. So that's going to give me r is equal to 2 minus 2 times the sine of negative theta. Now the goal is to simplify this and see if we can get back to the original equation in form. So what do I need to do here? Well, I have the sine of a negative angle. I have my even and odd rules that allow me to deal with a situation like this. So we know that the sine is an odd function, which means if we take the sine of a negative angle, it's the same thing as the negative version of the sine of that original angle. You can kind of think of it as the negative factoring out. That's not actually what's happening, but it's kind of what it looks like. So this negative will now become a part of this term, which means this negative sign here will combine with this negative when we apply that odd rule. And so we'll have r is equal to 2 plus, it switches the sign, plus 2 times the sine of theta. And so we get back to something that doesn't actually match the original equation. Notice the sign in the middle changed. So what we conclude from that is we can't conclude anything. We say that the test is inconclusive. It doesn't necessarily mean that when we graph this equation, we're not going to have polar axis symmetry. It just means that the symmetry test didn't give us that information. We would say that this test is inconclusive. Okay, now let's check for symmetry with respect to the line theta is equal to pi over 2, which again is kind of like the y-axis. So here we're going to take theta and we're going to replace it with pi minus theta. So same as before, sub in place of theta. So we have r is equal to 2 minus 2 times the sine of pi minus theta. Okay, so we need to simplify that function. Now I have the sine of something minus something else, which means I'm going to have to apply the sine difference formula. So I'm going to go out to the side and I'm going to work with that by itself. So just the sine of pi minus theta. Now we know the rule for sine of a difference is going to be the sine of the first angle times the cosine of the second angle minus the cosine of the first angle times the sine of the second angle. So this is going to be the sine of pi times the cosine of theta minus the cosine of pi times the sine of theta. So cosine of theta, sine and theta, those are variable. We don't know what theta is, but sine of pi and cosine of pi, those are going to be constants. We can determine what those are based on the unit circle. So the sine at pi radians, the x-coordinate, the y-coordinate at pi radians is going to be 0. So this is going to be 0 times the cosine of theta minus the cosine of theta. Well, the x-coordinate at theta is going to be -1. So be careful here. Subtraction results from using the difference formula, but the cosine of theta, or the cosine of pi, is also a negative number. So we have two negatives involved here, times the sine of theta. So of course this term goes to 0. Those double negatives we're going to combine and give us a positive. So +1 times the sine of theta, which is just going to be the sine of theta. So all of this just simplifies down to the sine of theta, which leaves us with r is equal to 2 minus 2 times the sine of theta, which means this test passes. It means when we graph this equation, our graph is going to have symmetry across the line theta is equal to pi over 2. In other words, what we kind of think of like the y-axis, any point to the right has to be matched by a point to the left. Okay, so that is going to help us when we graph. Now we want to check for symmetry with respect to the pole. So here we're going to take r and we're going to replace it with -r. So we have -r is equal to 2 minus 2 times the sine of theta. And the goal would be to simplify this and get it back to where it started. Maybe we could divide by a -1, but that's going to flip these two signs, which won't match the original. So there's nothing we can do here to take this equation and make it look like the original. So we would say that this test is also inconclusive. So based on our symmetry test, we can only definitively say that we have this one type of symmetry. With respect to that line, theta is equal to pi over 2. Okay, so now we're going to plot points, and using the result from that symmetry test, we're going to see if we can find a little bit of a time savings and not have to plot as many points. Okay, So again, starting at theta equals 0, and we're going to graph with theta in degrees just so it's easier to type into the calculator. Let's make a note of what we're graphing since I've moved the sheet. So r is equal to 2 minus 2 times the sine of theta. Okay, so theta is our input, r is going to be this expression involving our value for our chosen theta. So starting at theta equals 0, r is going to be 2 minus 2 times the sine of 0, which is going to be 2. So at 0 degrees or 0 radians, r is going to be 2. Now, how does the symmetry apply? Because remember, we have symmetry across this line. That means the whole line, both above and below the polar axis. Anything to the right is matched by a point to the left. So that means if we have this particular point on the second ring along the positive polar axis, that we have to have a matching point along the second ring along the negative polar axis. Now, what the symmetry test doesn't tell us is when we would actually graph this point. But it's reasonable to assume that if we graph this point for theta equals 0, then we would graph this point for theta is equal to pi. So ultimately, we should get to this point once we've rotated halfway around. Okay, so let's keep going. Now we're at theta is equal to pi over 6 radians, or 30 degrees. So r is 2 minus 2 times the sine of 30 degrees, which is going to be 1, exactly 1. So at 30 degrees, we're at 1, so the ring of 1. And again, using symmetry, we have a matching point on the other side of theta is equal to pi over 2 on the first ring. Okay, now let's go to 45 degrees. So 2 minus 2 times the sine of pi over 4 radians, or 45 degrees, so about 0.6. So at 45, here's where it's going to get a little tough to graph because everything is in there really close. About halfway, I'm just going to graph it as a small point. And again, we have a matching point on the other side using symmetry, so something like that. Now what happens when we get to 60 degrees? So 2 minus 2 times the sine of 60 degrees is going to be 0.2679, so really small, okay? So rotating around, here we go, in really close, so about right there, really close to 0, really close to 0, getting closer and closer and closer. And then what happens when we get to 90? So 2 minus 2 times the sine of 90 degrees is going to be 0. So that takes us to the pole. Now we can't use any symmetry to graph another point from here since it's along our line of symmetry. So what do we have so far? Let's trace the graph we have so far. So we started here. Once we make it to 90 degrees, just to verify that when we continue to rotate, we're getting those points that we've already plotted. So 2 minus 2 times the sine of our next angle, which would be 120. Well, notice that gives us the matching point that we just plotted. So this next set of points does, in fact, result from just continuing to rotate from pi over 2 to pi radians. So that means any additional points we're going to get are going to result from rotating past 180 degrees. So if we kept rotating, say we go to 210. So 2 minus 2 times the sine of 210 degrees, it's going to give us 3. Okay, so at 210 degrees, or 7 pi over 6 radians, we're out at 1, 2, 3. So that's if we continue rotating from here. Okay, the next one would be 225. So 2 minus 2 times the sine of 225, about 3.4. Okay, so here's 3, and about halfway between 3 and 4. Okay, keep rotating. So 210, 225, 240. So 2 minus 2 times the sine, 240 degrees, about 3.7. So notice the increase is slowing. So they're at 240. We're at about 3.7. So maybe around here. And then if we keep rotating, what happens when we get to 3 pi over 2 or 270 degrees? So 2 minus 2 times the sine, 270. Well, let's think about this one. So at 270 degrees, the sine has a value of -1. So -1 times -2 is going to be a positive 2. So 2 plus 2 is 4, not surprising. So 1, 2, 3, 4. Now we haven't used any symmetry yet, but let's go ahead and use that. So as we continue rotating, we have these points to the left of our line of symmetry, which means they also have to be matched by points to the right. So we're on the third ring at 210. That would be matched by something on the third ring over here. So we have a matching point right here. And we have a point here, which is going to match to the same location on the other side. And then another matching point. And then we meet in the middle on that line of symmetry. And so if I continue tracing, we're going to have a graph that looks like that. So I think it looks kind of like a lima bean, if you've ever had any lima beans. What we actually call this is a cardioid. And you can probably guess from the root of that word why we're calling it a cardioid. It's shaped like a heart, so it's a heart-shaped graph. Cardio for heart, cardioid for a heart-shaped graph. Now where did the graph start? This was the original point right here, and then we rotated from there, and after we rotate a full 2 pi radians, we make it all the way back to that original point. So if we continue to rotate, we would just continue to trace those points that we already have. Okay, let's try another example. Okay, similar structure. We've changed the trig function, and now our coefficients are different. It's going to be important to pay attention to. So we have a coefficient of 3, a higher coefficient, and then a lower number added on as a constant. So we've changed a couple things. We changed the trig function. We changed how these two coefficients are related. What else did we change? We went from having a negative between them to having a positive between them. So let's see what happens with this graph. So again, we want to check for symmetry first, see if that saves us a little bit of time. So symmetry with respect to the polar axis. So now we're going to take theta, replace it with negative theta here in our function. So r is equal to 2 plus 3 times the cosine of negative theta. Now cosine is an even function, which means the cosine of a negative angle is the same thing as the cosine of the positive form of that angle. So this is going to be the same thing as r is equal to 2 plus 3 times the cosine of positive theta, which matches our original equation. So that tells us that yes, this particular equation's graph is going to have symmetry with respect to the polar axis. So that means every point above the polar axis is matched by a point below the polar axis. Okay, now let's check our other two types of symmetry. So symmetry with respect to the line, theta is equal to pi over 2. So now we're going to take theta and replace it with pi minus theta. Okay, so cosine of theta replaced with cosine of pi minus theta. So r is equal to 2 plus 3 times the cosine of pi minus theta. Okay, same thing as before. I want to go out to the side, and I'm going to see if I can break this down, again using in this case the cosine difference rule. So the cosine difference rule says take the cosine of each value and then flip the sign, S-I-G-N, so our subtraction becomes an addition. And and then we have sine of pi times the sine of theta. Okay, so the cosine of pi radians, our cosine is -1. So that's going to be -1 times the cosine of theta. And then our sine at pi radians is going to be 0. So 0 times the sine of theta. Okay, so this particular term goes away, and then this will just become negative cosine of theta. So what happens if we plug that in here? Well, that's going to make this entire term, which was positive, negative. So that's going to become r is equal to 2 minus 3 times the cosine of theta, which does not match the original equation. So we conclude that this test is inconclusive. We can't officially say whether or not we have this type of symmetry just by the symmetry test. And then our last test with respect to the pole, we're going to take r and replace it with a negative r. So negative r is equal to 2 plus 3 times the cosine of theta. And just like with the previous example, if we divided out that -1, that would make our r positive, but it would also flip the signs over here, which means we wouldn't match the original equation. So this test is also inconclusive. So when we graph this one, we plot points. We're going to have symmetry with respect to the polar axis. So everything that's graphed above the polar axis is matched by a point that's graphed below the polar axis, and vice versa. So let me write down our equation. So r is equal to 2 plus 3 times the cosine of theta. And let's plot some points. Okay, so starting at theta is equal to 0. 2 plus 3 times the cosine of 0 is going to be 5. Okay, so at 0 radians, 0 degrees on the 5th ring. So that's the starting point. Now we can't use symmetry yet here because we're on our line of symmetry. So let's see what happens when we get to pi over 6 or 30 degrees. So 2 plus 3 times the cosine of 30 degrees, about 4.6. Okay, so at 30 degrees, we're about halfway between the 4th and 5th ring, a little bit closer to the 5th ring. Now here we can use symmetry. So if we reflect this across the polar axis, we're going to have a matching point right here, equidistant below the axis. Okay, now 45. So 2 plus 3 times the cosine of 45 degrees, about 4.1. So about here. And again, matching point on the other side of the polar axis. Now 60 degrees. So 2 plus 3 times the cosine of 60 degrees. 3.5 exactly. And again, we have that matching point, 1, 2, 3, 3.5 on the other side. And then what about 90? 2 plus 3 times the cosine of 90 degrees is going to be there at 2. So once we get to 90 degrees, pi over 2 radians, we're on the second ring. Flip it across, get the symmetric point also on the second ring below. Now how would we generate these points? More than likely these points will be generated once we get to 270 and would continue around to 360. So that means we still need everything from 90 down to 270 in order to complete everything over here on the graph. But that did save some time in terms of the total amount of graphing we have to do. So let's keep going. So now we're to 120. So 2 plus 3 times the cosine of 120 degrees is going to take us to 0.5. So 120. We're halfway between the pole and the first ring, which means we're also doing the same thing on the other side of the polar axis. Once we get to 135, 2 plus 3 times the cosine of 135 degrees. Now we're negative. Okay, so something unique has happened here. So we make it all the way around to 135 degrees. And now we're on the negative side, which means we're plotting on that ray, but on the opposite side of it. So something right about there. And again, we match it above and below the polar axis. So let's trace what's happened so far, just so we're clear what's happened. What does this mean? At one location, when we were at 120 degrees, we had a positive value for r. Once we made it to 135 degrees, we had a negative value for r, which means somewhere in between those two, we have intersected the pole. We've hit the pole. And once we hit the pole, we crossed over and we're located at this point. So let's trace the points we have so far, just from plotting, just so we're sure of what's going on. So we got here, once we hit 90, 120, we were still positive. And then when we got to 135, we crossed over. Okay, so now let's keep going. So past that, 2 plus 3 times the cosine of, next thing would be 150. And that's going to take us to negative 0.6, roughly. So 150, okay, we're at negative again, so negative 0.6. So at 150 degrees, but now we're plotting on the opposite side. So somewhere about here. And again, we have a matching point that's symmetric on the other side of the polar axis. And then what happens if we get to 180? 2 plus 3 times the cosine of 180 degrees. And that takes us to negative 1. So at 180, we're at negative 1. Now just to be sure, to make sure we're, again, then tracing points we already have, what happens if we went to 210? So 2 plus 3 times the cosine of 210 degrees. Where would that take us? So when we're at 210, we're at negative 0.6. So that would be along this ray. But the opposite side, which would take us to right here where we've already plotted a point. And so once we get past 180, we're going to cycle around to the points we got via symmetry. So you'll notice there is very definite rotation here. We go all the way around, we pass through the pole somewhere between 120 and 135 degrees, and then we continue rotating and we create a loop. In this graph, we create a loop. So once we get to 180 degrees, we've drawn half of the loop. Once we continue rotating, we complete the loop, come back to the pole, and then rotate outward again. And so this is going to be our graph. So notice it's similar to the one we graphed before in shape, but whereas the one we just graphed before stopped at the pole and then bounced back. Essentially we have the same kind of rotation, but it stopped at the pole and then bounced back. This one actually passes through the pole, creates a loop, and then cycles back outward. So those two graphs are very similar to one another with that one distinct difference. This is what we call a limachon. And it also makes me think again of the word lima bean, and it's got the little curly thing under the C. I don't know what that's called. But specifically, this is a limachon with a loop. It has a loop in it. So the term limachon is the general term for this class of graphs. This is one type. A cardioid is also a special case of the category of graphs that we call limachons. So the consistent thing between all these equations that will generate these types of graphs is we're going to have either our cosine or our sine with a coefficient plus or minus another constant added on. That's going to give us something of this particular type. So we can generalize what we're going to see in this case based on the values for A and B, for those constants in the problem. So anytime we have an equation of this form, so two constants A plus or minus B times either the cosine, or this should be the sine, either the cosine or the sine, this represents what we call a limachon. Okay. So case 1, we're going to break it down based on how A and B relate to one another. So if A is less than B, well, that's represented by the case we just saw. So in this case, our A is 2 and our B is 3. So A is less than B. If that's the case, our graph is going to have a loop generated when we pass through the pole. Now, if they are equal, that's what happened with our previous one. Now, we don't think of the negative as going with the 2. Think of it just as positive 2 minus another positive 2. So A and B would be the same. If that's the case, the graph is a cardioid. In other words, it's a heart, but it looks like a lima bean. Now, if B is less than A, okay, so A is bigger, but A is also less than doubled B, which we didn't do an example of that, but we could also have numbers that are related in that way. Then it's a lima bean shaped graph, but it has a dimple. Just to help you visualize what that looks like if you were to look at the cardioid graph. If you imagine taking that point where we hit the pole and then jump back, imagine taking that point and sliding it out so that it doesn't quite hit there at the pole, but it still is an indentation before we bounce back and continue rotating. That's what we would refer to as a dimple. So it doesn't come all the way into the pole, it's a little bit above the pole. And then the other possibility, if A is greater than or equal to 2B, so A is bigger than B and it's more than double the value for B, then we say that the graph is convex. So it's a limation, but it is convex. And again, if we were to visualize that from the cardioid, essentially what that means is if you imagine taking the point there at the pole, making it a dimple, if you continue to push the dimple outward, you essentially have a flat spot at that particular location. So it would basically look like an egg. So we have a flat spot on the bottom, and then it essentially looks like a circle for the rest of the graph with that flat spot on the bottom. So we would say it's a convex limation. So anytime we have an equation of one of these two forms, we're going to expect one of these 4 variations just based on the values we see. Okay, we're going to look at one final category of polar graphs. What happens when we have a coefficient on theta? So we've seen a couple different situations where our trig function has a coefficient. Well, what if theta has a coefficient? Now, from the standpoint of just graphing a trig function by itself, we know that putting a coefficient on theta is going to change the period. In other words, we complete cycles for our trig function, in this case, in a shorter period of time. So we would take our coefficient, divide the original period by that value. So in this case, sine has a period of 2 pi. We would divide the period by 2, which means that sine completes one cycle within half the time, within pi radians rather than 2 pi radians. That's going to have specific implications for the graph. It means we graph more within a certain distance. So that's going to essentially allow us to rotate further within our particular range that we're graphing. So we're going to see a lot of rotation, a lot of additional rotation with functions of this form once we add on a coefficient for theta. So let's check for symmetry for this one, and then we will graph it. So symmetry with respect to the polar axis. So we're going to take theta, and we're going to set it to negative theta. So that's going to be r is equal to 4 times the sine of 2 times negative theta. A better way to write that would be 4 times the sine of negative 2 theta. And as we've seen before, we know that sine is an odd function. So the sine of a negative angle is going to be the same thing as the negative sine of the positive version of that angle. So it would make this whole term negative, which means we don't match our original equation. That means our symmetry test is inconclusive. We don't know if it has that type of symmetry based on the test. Now what about the line theta is equal to pi over 2? So we're going to replace theta with pi minus theta. So we have r is equal to 4 times the sine of 2 times pi minus theta. Be careful when you write this. Notice I'm using brackets and parentheses so I can differentiate the two. So this is going to be r is equal to 4 times the sine of 2 pi minus 2 theta. Now I can actually approach this particular simplification in a couple of different ways. So I can use the sign difference formula like I did before, but there's an alternative approach as well. Our trig functions also have periodic rules that tell us what happens when we take a particular angle, a particular argument, and either add or subtract a full period. Well, the period for sine is going to be 2 pi. Which means all of our values for sine repeat after 2 pi radians. So what that means is that the sine of 2 pi minus 2 theta, well, the 2 pi doesn't actually do anything. It doesn't affect the value for sine because it just represents taking a full rotation and getting back to where you started. In other words, the value for the sine will be the same. So technically, we can essentially just forget the 2 pi, just based on that periodic rule for sine. Well, we know what happens when we have sine of negative 2 theta because we just encountered that problem. It means we have negative 4 times the sine of 2 theta, just as is. And again, we can't get that to match our original equation, so this test, unfortunately, is also inconclusive. And then for the pole, we're going to take r, replace it with negative r. So we have negative r is equal to 4 times the sine of 2 theta. And again, as with the examples we've already seen, there's nothing we can do to get rid of this negative without changing the other side of the equation. So this test also inconclusive. So unfortunately, in this case, our symmetry tests don't give us any additional information about our graph. So we're just going to have to graph it by plotting points. So let's write it down. So r is equal to 4 times the sine of 2 theta. Okay. So here we go, just plotting points. Starting at theta equals 0. So 4 times the sine of 2 times 0. Notice we're multiplying inside of the trig function. That's just going to be 0. So it's 0 radians. Our r value is also 0. So we have a point at the pole. Okay, what happens if we increase to 30 degrees or pi over 6 radians? R is going to be 4 times the sine of 2 times 30, which is going to be about 3.5. So at 30, we're at 1, 2, 3, about 3.5. Okay, now once we get to 45, 4 times the sine of 2 times 45 is going to be 4. So when we get to 45 degrees, pi over 4 radians, we're on the 4th rank. Okay, once we get to 60, 4 times the sine of 2 times 60. Ooh, notice we have a symmetric value. So once we get to 60 degrees, pi over 3 radians, we have the same r value that we had just a moment ago. So we have something right there. What happens when we get to 90? So 4 times the sine of 2 times 90 degrees, which is going to generate a 180 degree angle, is going to give us 0 again. So what does that give us so far if we just follow that rotation? So we started at the pole, we rotated here, rotated back around. Again, we had a similar value for r. It was symmetric right there across that line. And then we came back to the pole. So far, we have something like this. That's going to be our shape so far. So a little bit of rotation. And that is just what happens from 0 to 90 degrees. Now, if we continue to rotate, that'll take us to 120 degrees. So 4 times the sine of 2 times 120, well, that gives us a negative value. Now notice it's similar to the values we had above at about 3.5, but it's going to be negative. So there at 120 degrees, we're at negative 1, 2, 3, about negative 3.5. So we're rotating from the pole back around here. Now once we make it to 135, 4 times the sine of 2 times 135 degrees, so negative 4. So at 135, we're at negative 1, negative 2, negative 3, negative 4. So we also have a symmetric point right there. And then when we come to 150, 4 times the sine of 2 times 150 degrees. Again, matching point, matching value. So right there. And you can probably guess what's going to happen when we get to 180. So 4 times the sine of 2 times 180 degrees is going to take us to 0, back to the pole. So we continue rotating around. Keep going. And it takes us back to the pole. So you'll notice what we have so far does have symmetry with respect to the polar axis. The test failed. We couldn't actually use the test to verify any symmetry. But so far, the graph does look like it has that type of symmetry. That's why we say that the tests are potentially just inconclusive. A test failing does not mean that our graph won't have a certain type of symmetry. It just means we can't verify that from that particular algebraic test. So let's plot a couple of more points, and then we'll just use the symmetry we're seeing in order to finish it out, because you're going to notice the same kind of pattern occurring. So once we get to 180, now we're at 210. So 4 times the sine of 2 times 210. And that's going to give us 3.5 roughly. So again, seeing that repeated value. So they're at 210. We're at 1, 2, 3, 3.5. And then 4 times the sine of 2 times 225. We're at 4. And again, you can probably guess what's going to happen from there. We're going to have another point there. It's going to cycle back to the pole. So let's think about the kind of rotation we've seen. How is it rotated so far? So we rotated around this way, and then we dropped down, rotated around, and then we rotated here, rotated around. We'll get back to the pole. And you can probably guess what's going to happen on the other side when we continue rotating. We're going to have points here, and here, and here. We're going to rotate around, and then it's going to come full circle. And then if we were to continue rotating, we'll start repeating values. So this particular graph actually does have a couple of different types of symmetry. As a matter of fact, it actually has all 3 types. So we have symmetry across the polar axis. We have symmetry across the line theta is equal to pi over 2. And even though we failed the test for polar symmetry is a radial symmetry. So it means we have essentially symmetry in both ways. So this particular graph looks like a little clover. It does actually have the symmetry that we expect to see, even though the tests all failed. So kind of interesting. Okay, let's do one other similar to this. So what I want you to pay attention to, so number 1, this was the sine function, and then we had a coefficient of 2 on theta. Now where did the 4 come into play? The 4 came into play when we looked at the furthest out ring that these loops reached. So we reached the 4th ring for each of these loops, and that came from this 4. The 2 plays a different role, and we'll talk about that just a minute when we look at our next graph. So we've looked at a sine, let's look at a cosine, and let's change the coefficient on theta. So now it's not a coefficient of 2, it's a coefficient of 3. So let's check this one for symmetry. So with respect to the polar axis, so theta we're going to replace with negative theta. So we have r is equal to 2 times the cosine of 3 times negative theta. So that's the same thing as r is equal to 2 times the cosine of negative 3 theta. We know cosine is an even function, so it essentially eliminates our negative. So r is equal to 2 times the cosine of 3 theta, which matches our original equation. So we do have polar axis symmetry. Now what about theta is equal to pi over 2? So now we're going to take theta and replace it with pi minus theta. So 2 times the cosine of 3 times pi minus theta. That's going to be r is equal to 2 times the cosine of 3 pi minus 3 theta. Now, unfortunately, the shortcut we used with the previous example, let's go back and look at that for a moment. Rather than using the sine difference formula when we got to this point, we just recognized that sine has a period of 2 pi, so adding or subtracting 2 pi from an angle doesn't affect the value for sine. It has no impact on the value. So essentially it just cancels out. And then sine, of course, is an odd function, which makes the whole term negative if we allow a positive angle. So this case, we were able to use this rule because the period of 2 pi appeared. Now here we have a 3 pi. Cosine does not have a period of 3 pi, which means that shortcut does not apply in this case. In this case, we have to use the difference rule for cosine. So we have cosine of 3 pi minus 3 theta. And again, the difference rule tells us, break that up, that's going to be the cosine of each. So cosine of 3 pi, cosine of 3 theta, plus the sine of 3 pi times the sine of 3 theta. Now 3 pi, that is coterminal to pi. So just to have a circle to look at, if we're talking about 3 pi, that's one full rotation, that would be 2 pi radians. And then if we add on another half rotation, that'll take us to 3 pi radians, which is coterminal with pi radians. So the cosine and sine of 3 pi, that's the same thing as the cosine and sine of pi. So at pi radians, we know our cosine is going to be -1, and our sine is going to be 0. So this is going to be -1 times the cosine of 3 theta plus 0 times the sine of 3 theta. So 0 times anything, that term goes away, and this term just becomes negative. So negative cosine of 3 theta. So if we substitute this back into our actual equation, it's going to make the whole thing negative. So r is equal to -2 times the cosine of 3 theta. So comparing to our original equation, they do not match. So we would say that this test is inconclusive. And then symmetry with respect to the pole, we're taking r, replacing it with -r. So -r is equal to 2 times the cosine of 3 theta. And as we've seen before, again, we divide out that -1, it changes the sign on the other side. There's no way to get rid of it and result in an equivalent equation to what we started with. So this test, also inconclusive. But we can use that polar axis symmetry to save us a little bit of time. So we'll see how that's going to help. Okay, so let me write down our equation. So r is equal to 2 times the cosine of 3 theta. we're going to plot points and use our polar axis symmetry. So 2 times the cosine of 3 times 0 radians, starting at 0. Somehow I added an extra set of parentheses. Here we go. So that's just going to be 2. So they're at 0 radians. We're at 2. Okay. Now we go to 30 degrees, pi over 6 radians. So 2 times the cosine of 3 times 30 degrees. And that's going to take us to 0. Okay, so at 30 degrees, we're at 0. Now it may help to know what happened in the middle. So we went from here to here. Well, what happened in between 0 and 30? So let's see what would happen at 15. So 2 times the cosine of 3 times 15. So that would be halfway between 0 and 30. What's happening there? Well, we're about 1.4. So they're at 15 degrees, halfway between, we're at about 1.4. So something like that. So what's happened so far? Well, we started here, we've rotated around. Just to give us a sense, fill in the blanks in the middle. Okay, so we made it to 30. Now let's look at 45. So 2 times the cosine of 3 times 45 degrees, negative 1.4. Okay, so at 45 degrees, we're at negative 1 and about negative 1.5. So down here. And I'm going to keep filling things in as we go. So we're continuing to rotate. We got to there. Okay, then we make it to 60. So 2 times the cosine of 3 times 60. It's going to take us to negative 2. So it's 60. We're there at negative 1, negative 2, which is going to take us right there. So we continue to rotate. And then we make it to 90. So 2 times the cosine of 3 times 90 is going to take us back to 0. So once we get to 90 degrees, we're back at the pole. So we've rotated around and we rotated back to the pole. Okay, so where are we? We've graphed all over the place, but in terms of rotation, theta is at 90 degrees. So now we take theta to 120. So 2 times the cosine of 3 times 120 degrees. It's going to take us to 2. So at 120 degrees, we're at 1, 2. So this rotated around, we're at 2. Okay, next angle, 135. So 2 times the cosine of 3 times 135. About 1.4, we see that repeated value. So 135, we're at 1, about 1.5. Okay, so we continue to rotate. Keep going. So the next angle past 135 would be 150. So 2 times the cosine of 3 times 150. And that takes us back to 0. So back to the pole. So notice we filled in 2 loops, but we still haven't completed the loop we started at the beginning. So what's going to happen when we get to 180? So 2 times the cosine of 3 times 180 is going to take us to negative 2. Okay, so what does that mean? Well, we're at 180, but negative 1, negative 2, which means from where we were, we rotate back to this point, and notice that finishes that loop. So if we continue to rotate, what's going to happen? So the next angle would be 210. So 2 times the cosine of 3 times 210 degrees. So that's going to take us to 0, which is just rotation back where we started. So we completed the loop and then we keep rotating. So notice these 3 loops we completed in 180 degrees, pi radians, whereas the previous one we did, we had to rotate all the way around, all the way from 0 to 2 pi to finish the loops. So in this case we have 3 loops rather than 4. So we have a 4-leaf clover here. We only have a 3-leaf clover here. Now where do the 2, where do the 3 come into play? So the 2 and the 3. In this case, the 2, just like with the previous one, the 2 gives us the length of each loop. And notice in this case we have 3 petals. We have 3 loops. We call these petals. Well, what happened with the previous one though? We had 4 loops, but this 4 corresponded to the length of each loop, not the number of loops. This value gives us the number of loops, but it was a 2 and we ended up having 4 loops. So it was a 2 and we had double that. We had 4 loops. Here it was a 3 and we had that exact number of loops. We had 3 loops. Well, that actually develops a pattern that we will continue to see if we were to generate numbers similar to this. So the significance is that in this case, the coefficient on theta was odd, and in the previous case, the coefficient on theta was even. It makes a difference. So what do we have here? These graphs are actually called roses. So any equation of the form r is equal to some multiple of cosine or sine, but the angle theta has a coefficient, something other than 1. That represents what we call a rose. And it doesn't really look like a rose the way we think of roses. They look more like daisies, if you're going to call it a flower, but honestly they look more like clovers than anything. Now what we need to focus on is how many petals they're going to be, because that's what seems to vary. So our coefficient here, I'm going to make a note of that. A is the length of each petal. If it's a flower, they have petals. The length of each petal, P-E-T-A-L, not P-E-D-A-L. And then the number of petals is dependent upon the value for n. So if n is an odd number, like in the example we just did, there are going to be that many petals. There are going to be n petals. So when n was 3, we had 3 petals. If n were 5, we'd have 5 petals, and then so on and so forth. Now when n is even, there's going to be 2n petals. There's going to be double that many petals. And that's what we saw with that sine one. So this is just a general survey of some of the more basic types of polar graphs we can get. Again, notice pretty much everyone had some type of rotational component to it. That's what polar coordinates are useful for. Anytime we have a graph that can be represented using rotation, polar coordinates are going to be helpful. Particularly these last couple of categories of graphs where they got a little bit more complicated. If we were to try to convert those equations to rectangular coordinates to x and y, we would find that the equations become pretty complicated. Whereas in this case, they were relatively simple equations just using r and theta. So these are situations where having r and theta is going to be helpful. It's going to make graphing a little bit easier, just using theta as your input, using r as your output. Now, of course, you can write any type of polar equation you want and graph it the same way we graphed here. You pick values for theta, plug them in, get the associated value for r, and just plot points. You can come up with some really crazy looking graphs. If you're curious about what different types of polar graphs might look like, I definitely recommend that you Google it. Tons and tons of different exotic looking graphs, and in general, these are kind of fun to graph.